How do you intercept beetle pests before they damage your trees? We set out to solve a pesky pest problem. Sappi, a global producer of paper products and owner of many trees, has recently experienced an escalation of damage to their eucalyptus plantations caused by the Gonipterus or eucalyptus snout beetle, a non-native pest. This beetle feeds on the leaves of eucalyptus trees and can cause significant defoliation. The sheer size of plantations makes early detection unlikely. Effective remote sensing systems harnessing satellite data will therefore be very valuable. We use a time series of public satellite data to train artificial neural networks that provide infestation estimates for all relevant plantations in an interactive dashboard. The Beating the Beetle dashboard is the front end of an integrated solution to support beetle infestation prevention and damage control. The solution supports the exploration of raw satellite data through time and inspection of model predictions, which can then guide field workers to inspect plantations physically or trigger preventative measures. In the background, the solution is the result of a variety of complex tasks, including the collection of satellite data, data filtering, aggregation and normalization, and final data training. Let's take a short tour of the individual components. The Sentinel-2 mission has produced images covering South Africa since late 2018 at a spatial resolution of 10 meters. The usability of satellite data is significantly affected by cloud cover and other technical factors, such that data preparation forms an important part of the process. Selecting a time step of 1 month for the time series, all available images between steps can be used to filter and extract usable data. Sentinel-2 metadata relating to cloud cover and vegetation are used to select the best overall images. The final sample is then extracted by applying a selection algorithm that selects identically located pixels with a better NDVI. In this way, while the final image may contain patches of cloud, clear plantation regions are effectively selected for. The multispectral band values exhibit annual seasonal variation. Each month's values are shifted by a factor representing normal deviation for that month. This means that a model trained on data spanning one part of the year can be used to evaluate other periods. We provide a set of trained models based on two distinct approaches, which we call pointwise and blockwise. In both cases, a time series is used in an effort to capture the trajectory of change over time. In a pointwise approach, each pixel or spatial point is analyzed as an input pattern through time. In training, the label assigned to a compartment is applied to each of its pixels. Gated recurrent unit and long short-term memory architectures were trained in this way, exhibiting similar performance. In application, the individual prediction values are averaged to assign a single risk estimate for each compartment. In the blockwise approach, we bootstrap a time series of fixed-size compartment blocks through time in order to preserve some of the spatiotemporal associations in the imagery. As in the pixel-wise approach, the label of the compartment is assumed for each block. After a train-test validation split, a convolutional neural network is then trained on these bootstrapped compartments. The practitioner can use model predictions independently or as an ensemble to motivate further action. The real-world performance test will come from physical inspection, based on which the relative accuracy of the models can be established and the most effective approach selected. Model predictions are presented in a data table at compartment level next to other compartment statistics, as well as an interactive map showing compartment geography and infection predictions. These assist the user in visually detecting clusters of high-risk compartments. To support granular inspection by a practitioner, the solution allows interactive visualization of the raw and pre-processed data. In particular, the dashboard displays all available static data per compartment, such as the spacing between trees, planting date, and expected felling date, values of each band in the multispectral satellite data through time, and aggregated statistics such as band means and average NDVI. The dashboard thus aids general monitoring and early detection, prompting timely intervention. By applying advanced neural network architectures to continuous satellite data, we add significant scope to plantation protection. One step closer to beating the beetle.